All right, so in 10.1, we learned the language of hypothesis testing, learning what the null hypothesis, the alternate is, what all the basic stuff is for hypothesis testing. In 10.2, we learned about hypothesis testing for a proportion and did a few examples there. Now we move on to 10.3, which is hypothesis testing for a mean. All right, and so just like with proportions, I'm going to lay out the steps where we should already be comfortable with the language from 10.1, and a lot of the steps actually are borrowed from 10.2 with some slight differences. So to hypothesis test for a population mean. Here are the steps. Step 1, set up HO and HA. And just so that everyone remembers, HO is the claimed mean. Should involve an equal sign. HA is the test against. Involves less than, greater than, or not equal to. So first step is the same, right? Set up HO and HA. HO, H naught, the null hypothesis, whatever you want to call HO, should involve an equal sign, just like before. And HA is the test against, so it should involve your inequality, less than, greater than, or not equal to. Note, since we're doing means, now write mu instead of the p's we've been using. Right, with hypothesis testing for proportions, we had things like HO was P equals 0.42. I think I did that for my gun example. We wouldn't be using P anymore for means. Things are going to look like that the null is, let's say the average is equal to, I don't know, 6.4. I don't know. That's a made up example. But you should be using mu now instead of P. P was for proportions. Mu is mean or average, right? Don't need those in the final notes. Okay. Step 2. So first step before was to find HO and HA, and the second step was to gather your statistics, right? And you found your P hat. Find, so second step here, the sample mean and sample standard deviation. These will often be given in the problem. And just so you guys remember, we use X bar for sample mean. So we denote X bar for sample mean. And we denote sample standard deviation as S for sample standard deviation. Now, often these are going to be given. I'm going to say you found a sample where you found a sample mean of blah, 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 and a sample standard deviation of blah, blah, blah. And so you're not going to have to calculate these yourself, but just keep in mind that I could if I wanted, and I'm pretty sure the project is this way, that I can give you a list of data and you can calculate these on your own, right? To find a sample mean, you would add up all the values from your sample divided by how many there are. And to find a sample standard deviation, we know how to do that too, right? You find the mean first, then you take each value minus the mean squared, add those all up, divide by n minus 1, take the square root of that, right? We know how to calculate these on our own from chapter, what is that, chapter 3. But I said in the confidence interval section 2, where you need these two things, I'm not going to make you calculate them because a lot of you have already shown that you know what you're doing in order to calculate mean and standard deviation by hand. So a lot of times I'm going to be given them, they'll be given in the problem. All right, so after you find your sample mean and sample standard deviation, just like in step 2 of hypothesis testing for proportions, you found your p hat. In this one, you find your x bar and your s. After you do that, step 3 is to find the z-score for your sample mean. Make sure to adjust the sample standard deviation. Similar to when using the central limit theorem. And what did we do? We calculated, we adjusted the standard deviation by taking s divided by root n, right? And the z-score is calculated using the adjusted standard deviation and the claimed mean as the mean in the z-score formula. So find the z-score. That was was it step 3 in proportions as well, where you also have to come up with a standard deviation formula. In proportions, it was square root pq over n. With means, you adjust your sample standard deviation by dividing by square root n, and then you calculate your z-score, r value minus the mean over standard deviation. The only thing is here is we're going to go out there and find our value is mean, and then the claim is also a type of mean. So we have our value is our mean, and the mean in our standard deviation formula we'll use is the claimed one. Just like with proportions, you use the claim in the z-score formula where the mean normally would go. All right, step 4, find the t-score from the student's t-distribution table. And the way you do this is if HA involves less than or greater than, the test is one tail. And if HA involves not equal to, the test is two-tailed. Now, this student's t-distribution table we use when we were calculating confidence intervals for means. And for confidence intervals for means, I said we are always going to use two tails. And I said in the confidence interval section, just use two tail. Don't worry about what one tail means. We'll get to that later. Well, now we're later, right? We use the one tail part of that chart if HA involves less than or greater than in hypothesis testing, and we'll use the two tail for not equal to. And what this boils down to and how you remember the type of tail is it is one tail when you only are going in one direction, right? So for instance, if I said I'm thinking of a number less than, see how I'm circling less than? If I'm thinking of a number less than 8, well, you know to go in one direction. You know to go, okay, I don't know, 7, 5. You know which way to guess. Same thing if I said I'm thinking of a number and it's greater than 14. Well, then you would know to go in one direction, right? You would know to go up. Whereas if I said something like, I don't know, I'm thinking of a number and it's not 20. It's just not equal to 20. Well, then you would have to decide on which direction you want to go in, and there's two ways to go. I'm thinking of a number and it's not 20. You could go up. You could start saying 21, 22, 23, yada, yada, yada. Or, since I didn't give you a direction, you could also say, I don't know, 19, 18, 17. So there's two ways you can go. And that's what the type of tail is, and it has to do with the normal distribution and the t-distribution, all that stuff. But just know that if it's less than or greater than, it's one tail, and if it's not equal to, it's two-tailed. And that's actually, retroactively, I can kind of give you the hint on why we use two-tail with confidence intervals, right? With confidence intervals, it's a type of not equal to. With confidence intervals, you say, I believe with 95% confidence that it's, the true value is between this and this. Well, there's two ways you could be wrong. Your range could be a little too high or it could be too low. And that is why confidence intervals use two-tail, because you don't know where the true the true mean is in regards to your interval. Your interval could be too high or it could be too low, so you don't know. That's why you use two-tail for confidence intervals. Whereas in hypothesis testing, you get a choice. If you're doing less than or greater than, use one tail. If it's not equal to, it's two-tailed. So going back to that T-chart, which is new, keep in mind that is on Blackboard for you to use, and it's also in the back of the book. Step 5, compare the z-score from step 3 to the t-score from step 4. If the absolute value of our z-score is greater than t, we reject the null hypothesis. If the absolute value of our z-score is less than or equal to t, we fail to reject. Fail to reject the null hypothesis. And that's it. And the book actually goes through a p-value method, and there is a way to use the chart kind of in a roundabout way to come up with a p-value similar to how we did proportions. But I find that this is a little bit easier for me to keep track of. Just know that if we have a big z-score, absolute value makes things positive, right? That's all that means. Basically, when you get to your z-score, don't consider negative or positive. Just think of the raw number. So absolute value of negative 1.6 is positive 1.6. Absolute value of 13.7 is 13.7. Absolute value just means don't look at the sign. But if your z-score is bigger than your t-score, I like thinking of t as threshold. If your z-score is greater than your t-score, you reject HO, which makes sense because big z-scores are super unusual. Just like when we were doing hypothesis tests for proportions, when you get a small p-value, that's unusual. That means we reject the null. Same thing here. If we get a big z-score, that's like a small p-value because large z-scores don't normally happen, right? Just like small probabilities don't normally happen. So if we get a large z-score compared to our threshold, we reject. If our z-score is less than our t-score, less than our threshold, we fail to reject HO. All right, and those are the steps. Set up your hypotheses just like before. Find your sample statistics, your sample mean and your sample standard deviation. A lot of times those are already going to be given because you've already shown you know how to calculate mean and standard deviation. a few weeks ago. Then you find your z-score. Make sure you adjust your standard deviation for your sample size, just like you did with central limit theorem, because we're involving more than just one person in our sample, right? And we're going to this t-distribution, which you need to adjust the standard deviation for. Then you find your t-score using that t-chart, that new chart. And the way you use that t-chart is just like normal. You need your significance level, which, like I said, we're always using 0.05. You need your degrees of freedom, which is one less than what was sampled. And then you need to know your type of tail. If HA involves the not equal to, it's two-tailed. Less than or greater than, it's one-tail. Then you compare what you got in step 3, your z-score, with your t-score from step 4. And if your z is pretty big, you reject it. So it's bigger than your threshold. And if your z is less than your threshold, you fail to reject. All right. Let me block off the steps right here. There's the steps. Let's go through at least 2 examples, right? All right. I'm going to try to pull one from the book. All right, let's see. Here we go. In 2013, the U.S. Census Bureau reported that what did they say? The average amount of time it took an adult to commute to work was 27.5 minutes. You randomly sample how many people? The book does a lot. I'm going to do lower that. You randomly sample 121 workers today and find an average commute time of 25.8 minutes with a standard deviation of 8.8 minutes. Conduct a hypothesis test with a significance level of 0.05 to determine if the average commute time has decreased since 2013. All right, so way back when in the dark ages of 2013, it was reported that average time it took people to get to work was about 27.5 minutes. And now 7 years later, you sample people, 121 people to be exact, and find an average commute time of a little bit less, right? 25.8 minutes with a standard deviation 8.8. and these numbers came from your sample, right? Out of these 121 people, you go and you add up how much all of the times they take to get to work, divide by 121, divide by how many there are, you get 25.8. And then similar for standard deviation, you can sit there and calculate it out yourself with a bunch of data, but I've decided to just give you the summary of the data right here. But anyway, you go out, you find the average commute time is only 25.8 minutes nowadays. And you're curious, you conduct a hypothesis test with a significance level of 0.05 to determine if the average commute time has decreased. Basically, you're seeing, okay, well, it only takes people 25.8 minutes to get to work nowadays. They said 7 years ago that it should take about 27.5 minutes on average for the average person in the United States. And you're curious if this 25.8 minutes is strong enough evidence to say that this is no longer the case, to refute this fact back from 2013. And I'm actually not quite sure if this is enough or not. And so we'll have to go through the math to see if this is statistically significant enough to refute this claim from back then. All right. Oh, it is worth noting too, just like with proportions, how we had to have conditions to make sure that the hypothesis testing process actually works. There are conditions for testing at population mean, and they're very similar to the conditions for the central limit theorem. That it has to be a simple random sample, that your sample size n is sufficiently large. I believe in class I said it was greater than or equal to 30, right, for central limit theorem. And the same independence condition. You want to make sure that your sample participants are all independent of one another. Basically, make sure that you didn't sample everybody from the same like bus going to work, right? That would make this not a great statistic to be using. So there are conditions that you should be checking here, but again, if it wasn't satisfying the conditions, I wouldn't be asking you this problem. All right, so let's go through the actual steps of the solution. So the first thing in my steps to hypothesis test the mean was to set up HO and HA, right? And we've done this a few times now. HO, HA. So what is the null hypothesis? Well, what was being claimed? What was being claimed back in 2013 was that the average time it took was 27.5 minutes. So they claimed that the average, notice I'm using mu now instead of p, right, because we're talking about averages, that the average time it took was equal to 27.5 minutes. And what are we testing against? Well, we're trying to determine if the average commute time has decreased since 2013. So we are curious to see if the average commute time, average being mu, is less than what it was in 2013, less than the 27.5, right? Just like with proportions, these statements should be exactly the same, right? The claim is that the average is 27.5, is meaning equals, and the alternate is we're testing to see if it's actually less than that, right? To see if it's decreased since 2013. So the hypotheses have been set up. Step 2 then, find the sample mean and sample standard deviation. These will often be given in the problem. So what is our sample mean and sample standard deviation? And are they given in the problem? Yes. You find an average commute time of 25.8 minutes with a standard deviation of 8.8. Like I said, I could give you the data and have you guys calculate those numbers yourself like I did in chapter 3. But I just gave them to you here. So you find your sample mean to be 25.8. Sample standard deviation, 8.8. All right, step 2 is done. That's all it was asking for in step 2, right? Find the sample mean and sample standard deviation, often given in the problem. And they were. Find the z-score for your sample mean. A lot of times this is called your test statistic as well. Make sure to adjust the sample standard deviation. So, step 3, we're going to adjust our sample standard deviation to 8.8 by dividing by square root n, which is how many people? 121. So we take 8.8 divided by the square root of 121, and that works out to be 0.8 exactly, actually. No rounding needed. So our standard deviation has been adjusted, and now we need to find our z-score. Our value we found was 25.8, right? That's what we found. Minus the mean. The claim goes here, right? What was claimed? What is the mean supposed to be? Well, they said it was supposed to be 27.5. Divided by the standard deviation. Well, we've adjusted it. The standard deviation after adjustment, 0.8. So our value, 25.8, minus the mean. Well, we use the claim as the mean, just like we did when we were doing proportions, 27.5. Divided by all of that, divided by 0.8. And I get a z-score of negative 2.125. All right, step 3. Oop, that was step 3. Step 4. What was step 4? Find the t-score from the student's t-distribution table. All right, so this is using that new chart that we first got when we did confidence intervals. So t-score equals, well, we don't know. To use the t-chart, you need to make sure you know your degrees of freedom, your significance level, and the type of tail, right? All right, so what are those 3 things? Is it a 1 tail or 2 tail? Oops. Well, since our alternate hypothesis is less than, if HA involves less than or greater than, the test is a 1 tail. So we are dealing with a 1 tail test. Your significance level that we are using is 0.05. That's also given in the problem. And even if it's not, you can always assume 0.05 because that's what I'm used to using. And what is our degrees of freedom? Just like with confidence intervals, degrees of freedom is 1 less than what was sampled. So it says we sampled 121 people, so our degrees of freedom is 120. So you need to line up 1 tail with 0.05 across the top, and then line that up with the row that is degrees of freedom 120. And all of that together produces a t-score of 1.658. Just line up 1 tail with 0.05 across the top. So look over at 1 tail until you see 0.05. And on the t-chart I posted on Blackboard, it's the first slightly darker shade of blue column. And then in that column you look down until you get to degrees of freedom 120. And you get a t-score of 1.658. And now step 5. Step 5 asked to compare the z-score from step 3 to the t-score from step 4. You compare your absolute value of your z-score, just the raw number. Don't worry about the sign. Absolute value of z compared to t. If it's bigger than t, we reject. If it's less than t, we fail to reject. So, since our z-score is equal to negative 2.125 and our t-score is equal to 1.658. Which of those cases is true? Well, the absolute value of our z is just regular 2.125, right? Absolute value means get rid of the sign. Just make everything positive. So 2.125, compare that to 1.658. Which one's bigger? The 2 is bigger. That's not a good greater than sign. The 2 is big. The 2.125 is bigger than 1.658. And what did it say to do when our z-score was big? Well, big z-scores are just like small probabilities. They don't happen unless something is a little wacky. And the only thing that's wacky is we assume the claim is true until proven otherwise. So we reject HO. So since our z-score is bigger than our t-score, we reject the null hypothesis. So what does that mean? Again, I like rewriting the hypotheses as I had them in step 1. The null hypothesis was that the average commute time is equal to 27.5. And the alternate was that the average is less than 27.5. And what did I end up doing? At the end, I am ending up rejecting HO. I don't believe this. Right? I am rejecting the null hypothesis. I do not believe that the true average commute time is 27.5. What do I believe? What does evidence suggest? Evidence suggests the alternate is true. I believe this. Oops. So, if I were to answer the question, conduct a hypothesis test with a significance level of 0.05 to determine if the average commute time has decreased since 2013. Has it decreased since 2013? It sure looks like it. I believe that the true average commute time is less than what it was back in 2013, which was the 27.5. So yeah, I believe average commute time has decreased because I reject the idea that it is equal to 27.5. Maybe do one more example. Let's see. What did they do in the book? They did the commute time. And let's see. So I just want to make sure I get a good example going here. Okay, here we go. We're going to use average heights. Zoom in. The average height of adult males is 69.5 inches. You randomly sample 43 adult men and find an average height of 70.78 inches with a standard deviation of 2.77 inches. Conduct a hypothesis test. To determine if the average adult male height is different from the claim of 69.5 inches. use a significance level of 0.05, just like always. All right, so average heights claimed to be 69.5. You randomly, I'm going to put that in quotes because I got this 43 adult men from the book, which wasn't random. 43 adult men find an average height of 70.78 inches, standard deviation 2.77, conduct a hypothesis test to determine if the average adult male height is different from that claim of 69.5 inches. And we're using a significance level of 0.05. So again, label in the steps, set up the hypotheses, HO and HA. The claim is that the average is equal to 69.5. And the alternate is what? What are we testing against? It's just asking, is it different? So since it's not asking for greater than or less than, I'm just going to put not equal to 69.5. Is it different than that claim of 69.5? Doesn't care if it's less than or greater than, just is it different? Step 2. What was step 2 above? It was find your sample mean, sample standard deviation. Those are usually given in the problem, which they were here as well. You went out and sampled, you found 70.78 as the sample mean, and as the sample standard deviation was 2.77. Step 3 was find the z-score. Z-score is our value minus the mean over standard deviation. Standard deviation needs to be adjusted though. So you will take the old standard deviation, 2.77, divide by square root n. N, how many did we sample? 43. And 2.77 divide by the square root of 43. Gotta put that into the calculator really quick. Square root 43. I got 0.42. So now that the standard deviation's been adjusted, we can find our z-score. Our value we found was 70.78 minus the mean, they're claiming is 69.5, divided by the standard deviation after adjustment is 0.42. So our value, 70.78 minus the mean, they're claiming is supposed to be 69.5, divided by the standard deviation, 0.42. And we get a z-score of 3.05. Before I even continue, that's a pretty high z-score, right? That leads me to believe we're going to end up rejecting because big z-scores like this are not common. But we'll keep going. Step 4. Step 4 is to find our t-score. Well, to find our t-score, we need to know the type of tail, which in this case we're using two-tail because we're doing a not equal to. So it's two-tail. Always two-tail when you're not given a direction. Two-tail. What is the significance level? Significance level from the problem says 0.05, which I will always be using. And what was our degrees of freedom? Well, how many did we end up sampling? It says we sampled 43 adult men. And that means the degrees of freedom is 42. And now you'll go to your t-chart. And you look at two-tail, the two-tail line at the top, go over until you see 0.05. That'll be the second column. That's a slightly darker shade of blue. 0.05. And then you would look down until you find degrees of freedom for 42. And you'll notice we have a little bit of an issue. That there is no line for degrees of freedom 42. And whenever that happens, you guys might have guessed, you just use the next best thing. So since 42 isn't on the chart, because it's impossible to list every possible degrees of freedom, that you can't list every number, right? So you go down and you get as close to 42 as possible. I would use the line for 40. And on the line for 40, it says your t-score is 2.021. Now, if some of you rounded up to 60 for some reason, you know, since we would like to use 42, I think using 40 would make the most sense. But if you went to 60, the t-score ends up being 2.0000. Not that big of a difference from what I'm using here, huh? And that's what happens is when the numbers start to get high, the t-scores ended up getting closer and closer together. So Step 5, we compare the absolute value of our z-score with our t-score, our threshold. So since z is equal to 3.05 and t is equal to 2.021, the absolute value of our z-score, absolute value of 3.05 is just 3.05. Compare that to 2.021. Which one's bigger? The 3.05. When our z-score is bigger than our threshold, we reject the null hypothesis. So, what are we rejecting? I always like writing this part so I can interpret it correctly. They said that the mean is supposed to be 69.5 inches, that the alternate is that it is different from that. And what ended up happening, we ended up rejecting HO, so we do not believe this, do not believe the null, we believe the alternate. So, we believe the average height is different from the claim of 69.5 inches, right? We ended up rejecting that, and we're going to go with the alternate, that it's not equal to 69.5. And now if you do have a book, it's actually quite interesting because this 69.5 actually is true. If you do average out a bunch of male heights, you're going to get something close to 69.5. Why did my sample produce such a high height then? You know, these 43 adult men produced an average height. Maybe I just got some tall men in my sample. And I say that that's enough evidence to say that it's not 69.5 in the end. What's funny though is the book, this 70.78 actually does not come from a random sample. That's why I put randomly in quotes. This 70.78, these 43 adult men, that's the first 43 presidents of the United States, their heights. So it wasn't even random. And maybe presidents are just in general taller than the average American. Maybe it's easier for a tall person to get elected. I don't know. But this goes back to the biggest assumptions we make. One, we assume that the claim is true, but also what we've been assuming this entire class is samples must be simple random samples, right? I did all this math. I find out I'm going to reject this idea that the average American or average male is 69.5 inches tall. But my sample was not random. I got a lot of tall people in my sample. Like I said, I don't know. There might be some psychology thing part of this that elected officials are in general taller than the average person. I don't know. But this 69.5 is actually true, and I ended up rejecting it. So that is a type 1 error. And why did that type 1 error happen? Probably because my sample wasn't random. It wasn't a simple random sample. I just pulled up the list of presidents and their heights. That's not random at all. Which would make all of this stuff in the middle junk, right? Because it wasn't based off of a simple random sample. It was a good exercise though. Because remember, sometimes it's not clear that it wasn't a simple random sample, right? You're not always the one going out and collecting the sample, so even if these statistics from step 2 were obtained from a third party, maybe you read them in the news or something, I don't know, you're still assuming that they came from a simple random sample when in reality they might not have been. All right, so those were 2 examples of testing a hypothesis of means. It's a little different with proportions. Let me actually write this down because this is the biggest problem I find for proportions. Small p-value less than 0.05. That led to rejecting HO, right? And a bigger p-value, greater than 0.05, that led to failing to reject HO. So after the steps of proportions, you ended up with something called a p-value. When it was less than 0.05, you ended up rejecting. When it was bigger than 0.05 or equal to, you can actually throw that on there too. When it was greater than 0.05, you end up failing to reject. And for means, it's the opposite. Big Z-score, meaning Z is bigger than that threshold T. That led to rejecting the null hypothesis. And a small Z-score, Z less than T or equal to, led to failing to reject. And that is a huge difference. For proportions, you come up with something called a p-value, which represented a probability. Small probabilities lead us to reject what we assume to be true, right? Because small probabilities do not happen often. So since small probabilities do not happen often, we assume we made a mistake in our assumption, so we reject the original claim. A big p-value, big probabilities happen all the time. We're not concerned about that, so we don't think anything was wrong with our assumptions, right? For z-scores, it's the big z-scores we have to worry about, right? Big z-score, greater than that threshold t, that ends up rejecting HO because like small probabilities, big z-scores don't happen that often in real life. A z-score of 3 is unusual. So big z-score leads us to reject, whereas a small p-value is what leads us to reject. Small z-scores happen all the time. We're not really concerned with those. So since small z-scores happen all the time, we don't think anything's wrong with our assumptions. We don't reject HO. So it's opposite. Small p-value, reject. That's for proportions. Big z-score, reject. That's for means. And that is hypothesis testing for means and for proportions. These are not great problems considering there's multiple steps. And like I said, sometimes students have a hard time, even after all the math, they can do all the math steps and then have a tough time interpreting that. But I always find it easier to go back to the original hypotheses and write what you meant to do. In this case, reject HO, I get rid of it, I believe the alternate now. That is hypothesis testing. Next up, we will go back to chapter 4, which is correlation and regression. And in chapter 4, there is a type of hypothesis test we're going to be doing, and that's why I think it fits better here at the end of the semester versus at the beginning. But please, please, please make sure to do the practice problems, not just for proportions, but also for means. Switch it up. I will post practice problems for both on Blackboard. Make sure you attempt them on your own. You know, it's one thing watching my lecture and, okay, that makes sense, that makes sense, that makes sense. Make sure you're trying these problems on your own. All right, I will see you guys next time for correlation and regression, which does require StatCrunch. There's no way to do it by hand. So if you have not gotten StatCrunch yet or access, you need to buy it now. It either comes with the textbook or you can buy Axos Code on your own. A lot of what we've been doing all semester, we've been able to do by hand. Literally the next lecture, we will not be able to do it by hand any longer. So please, please, please make sure to get StatCrunch now. With that, have a good week.